Okay, so let's continue with our lecture today. Um, okay. Uh, uh, okay, so I think last time I said that, assume that we have so we have the W1 is equal to, uh, X1, where this X1 is in reals, positive. And then, uh, yeah, so for this W2 is equal to X2 plus RY2. Uh, sorry, it should be negative. And then X2, Y2, all positive. Uh, do I assume that they equal to zero or uh uh yeah, let's assume that they are strictly positive. Um, so this Y2 cannot be equal to zero, definitely. And then if this X2 equal to zero, then I think this X2 can be equal to zero, right? Yeah, folks. Um, okay. Uh, yeah, sorry, I didn't include the graph here. Uh, yeah, so this omega one is okay. Uh, so we want to do a rescale, right? So uh, uh, yeah, so we show the general case, right? So we show that uh, uh, the modulus of uh, sorry, n1 omega one plus uh, n2 omega two. Yeah, so we show the case where this omega one and omega twos are like uh positive or like has like a normal like this that's one, right, and then this omega two it has like width and height are equal to one. So uh I think there is a concept, but I forgot what the concept is. So motion to take equal to zero and or omega one is equal to one, and then omega two is equal to negative one plus I. Okay. Uh, and also this n1, n2 is bigger than equal to zero. Okay, so Okay, so right now, what do we do? So, uh, okay, so now for this omega 1 equal to x1, so basically, uh, mm, okay, so, okay, so, in, so let's call this star. Okay. So in the star condition, have uh, L1 W1 plus N2 W2, which is equal to um, L1 X1 plus N2 X2. Uh, What do you think? Um, so so if we put like the uh for S1 out. Uh, so yeah. Mm, yeah, so we have that inequality. Yeah. So yeah, we have the equation. And then yeah, so the thing is that what does this has something to do with terms here, right? Um, so can we do another same argument here? Um, yeah, I feel like we can do the same argument here. Uh, yeah. So um, So this is bigger than equal to uh okay, so you wait. Sh- I don't think I can do that. Uh, uh so x2 over x1. Uh okay, so let's see if we can just mimic the arguments as here. Uh uh yeah, I remember that. Um okay, uh so there is this argument about uh like for example, if you have uh n2 is equal to uh let's say x2 over x1 and 1, right? So uh then uh this part will cancel out, right? And then um so that's being said, you will have yeah, so you would have this error W2 being the same length as W1. So here we should have some upper bound for this N1 and 2. Uh, Uh, okay, so then, so the things inside the square root is just um, times n2 square. Uh, oh, okay. Okay, so yeah, so this is a relation between n2 and 1. So let's see. Um, so what is a number? Okay, so here, uh, yeah, so you would just like equal to x1 and to y2, right? Um, so here this n2 plus n1, okay. So here this n2 plus n1 is exactly the if you transfer everything into okay, so this is equivalent of saying n1 is equal to uh x2, oh sorry, x2 over x1 n2, right? Yeah, so if you transfer everything into n2, so I want a lower bound that's in terms of n2. So then this x over 2 over okay. So basically I pull out this uh I set it to the n1 as this one, okay, and then I add 1 to it. So then it becomes n2 times 1 plus x2 over x1. So can I actually multiply by some constant? I think so, right? So it's like n2. Uh, yeah. So I can certainly multiply some constant to make this term to be less than that. Yes. So there's definitely a constant. Okay. Yeah. So this is a constant that we start with. Okay. And then so uh then okay. So then let's see what happens if I move. Okay. So suppose that this n2 is fixed, right? So let's say fixed n2. Okay. Okay, fixed n2. Okay. So okay, so suppose that we are under this situation. Okay. So now first we fix n2. Okay. Uh, and then let's see what happens if this n1 is smaller, right? This n1 is like smaller. So uh, yes. So if the n1 is smaller, then what happens is that um, I think I need some space here. Uh, okay, let's see. So, uh, that's one and two. Okay. So now, uh, so we have the the inequality. Uh, x1 n2 y2, which is bigger than or equal to some k times uh yeah. So n1 plus n2. Okay. Maybe let me just write out the full version. Yeah, so this is just zero. Okay. So we will see that uh uh yeah, so this n1 is exactly x2 over x1 n2. Okay. So okay, so when you see that when this n1 is getting smaller, right? So this k times n1 plus n2. Uh so uh when this n1 is less than n2 over x1 times n2. So then uh so we have the k times x2 over x1 n2 plus n2 is strictly bigger than uh yeah, so strictly bigger than k times uh n1 plus n2. Okay. But then you see that the left hand side, right? So the left hand side, so and because right, so because when this n1 is getting smaller, so actually this term is positive, right? So then we have so what's it called? Uh, so and then but the right hand side is uh no uh and we also have that uh yeah, so let's call this L. Okay. So let's call this L of N1. Okay. And then this L of N1 is bigger than, yeah, strictly bigger than this, just this term here. Okay. X1 times N2 Y2, which is strictly bigger than, yeah, we show that this is bigger than or equal to this K times that. Yeah. So we have the container. Yeah. So which is bigger than this guy, right? Yeah. Okay. So now what happens if we have uh one is bigger? Yeah, I think we can like manipulate the argument. So um let me think. Um uh Yeah, what happens if this N1 is very big? Uh, let's see. So if this N1 is very big, oh, so I think we also have I think we, uh, oh, yeah. Okay, so let's see. Um, so suppose that we have N1 is equal to, uh, let's say, C times, uh, do I really need this? Um, let's keep that. Some constant C. So I want to analyze the situation for the C, right? So mm, okay, so yeah, so this becomes what? X1 times so this is just C minus one, right? So we instead choose N1 equal to C times that. Uh, over X1 of N2 and then squared, right? Uh, whole thing squared and then plus N2 squared, Y2 squared. Okay, so now uh yeah, so let's factorize this uh N2 out. Okay, so we have x1 times the square root of, so sorry, x1 times uh wait, shoot, did I? Okay, never mind. So yeah, so you have x1 times you take the let me think. Yeah, you factor the n2 out. Okay, and then you take the square root over uh okay, so for the left hand side, what you get is that you get c minus 1 square times this x2 square over x1 square. Okay, and then plus y2 squared, right? Okay. So what happened on the right hand side? So on the right hand side, uh, so on the right hand side, okay. So let me turn a little bit. So on the right hand side, you will have k times n1 plus n2. So n1, what is n1 plus n2? So n1 plus n2 is just 1 plus c times x2 over x1 n2. Uh, I mean, uh, so this is like the n1 plus n2 term. Uh, I think there's always a k, right? Yeah. Wait. No, 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 no. So for each C, there's a k, but is there a k for a uniform C, right? So I want a k for any C is true. So yeah, can I do that? Um, let me think. Okay, so then the question is, uh, does there? Okay, yeah. So I think the answer is definitely yes, but what is exactly the case? How do we repick it? Yeah. Does it there is a case such that for any C this holds, right? Okay, so let's see what happens if this C is very large. So when the C is very large, uh, you have the left hand side, the Siemens 1 squared, x2 squared, or x1 squared is large. But so this is like uh yeah. So what happened for the right hand side? Uh, wait. If this N1 is getting larger and larger, what will happen? Uh, K times N1 plus N2. Um, I think they actually converge, right? Because um, because they have the same growth rate. I think that's the reason, right? Yeah. So if you are letting C goes to infinity, uh, if you take the ratio between these two back to stuff, uh, it's gonna converge to a number, right? Uh, yeah. So okay. So if I take the limit, uh, So what happened? Guys, so with the limit work. Yeah, so let me think. So we'll have limits equals to infinity of the bottom one, top one, x1, and 2, take the square root of is c minus 1 square x square x2 square over x1 square plus y2 square over the bottom one, which is 1 plus c x2 over x1 n2. Okay, so we'll take the limit. You will get what? You will get um yeah. So what you get? Uh, okay. So this equals one. So if you expand it, you will get c squared minus 2c plus 1, right? And then what you do is that you divide by c on both sides. Um, yes. So because this c is let me think. Uh, yeah. So it becomes 1 over c plus x2 over x1 times n2. And then for the top part, what you have is that x1 to take the quotient you fit in, it becomes square root c squared. Then uh yeah, so these will all cancel out. So then what's left is just uh x2 square over x1 square. Yeah, so I just don't bother writing out writing out. Okay. So and again, this one more c is gone. Okay. Then is equal to so on the top you have n2 times x2, right? Uh, because the x1 they are cancelled out. And on the bottom part you will have n2 times x2 over x1. Yeah, you get x1. Okay. Um, wait. I think I just wrote. I think I didn't record this. Uh, yeah. Anyway. Yeah. Sorry. I didn't record this. Yeah. Yeah. What I'm doing is that I'm taking the limit of the upper one over the lower one. Okay. So I just calculated that if you like expand out this c minus one square term, and then this is gone. Yeah, so then this the only thing that is that just the c square term. Yeah, the c square term it corresponds to x square x2 square or x1 square, which you take the square root, then it becomes yeah, then multiply by x1 becomes x2, and then this n2 is here. And then on the bottom part you have x2 over x1 times n2. Okay. And then finally you will just get x1. Everything else cancels. So yeah, so if you let k to be just x1, right? So that means that this limit when c goes to infinity of this ratio is actually equal to 1, right? So does that tell you something? So that means that this, okay, that means um, this ratio is uh, close to 1 as c goes to infinity. So what does the ratio close to 1 mean? So that means that uh, uh, wait, so I want a lower bound. So how do I get a lower bound? So this ratio, okay, so if I have some ratio, let's say uh, AC over BC goes to 1, does that has create some necessarily some lower bound condition on this BC and AC? Okay, I think that's doesn't. Uh, if this AC over BC is actually converted to 1/2, what does that mean? That means that uh, when C is large, right, this AC over BC is very close to 1/2. So AC is ice. Okay. So this AC is roughly speaking, 2AC is like uh BC, right? Oh, yeah. So I think you can have that. But uh, yeah. So what happens if AC over BC goes to 1/2? Um, okay. Let's see. Okay. Yeah, I think it would indicate some containment relation. Yeah, when this C is large. Yes. Um, So if I know that they are all positive. Oh, AC is okay. Okay, so yeah, I think this argument will work. Um, because if you put like the AC at the top and then BC at the bottom, and then you see that you let the coefficient goes to 1/2. Remember for this scale, we can like manipulate this scale, and then so that there is a C large, so that the AC or BC minus 1/2 is less than epsilon for any C like being larger than the bounds. Okay, so this just implies that uh because this is positive, right? Wait, shoot. It really doesn't mean that. Yeah, take back my words because this term may not be positive, right? Uh, so what should I do here? Mm. So uh, it's 0.01 half. Oh, okay. Wait. Okay. Yeah, so you will get the if you know PT is positive. Okay. Yeah. So you get a upper bound for this lower bound. So if you treat the this one as a BC, right? Um, yeah. So here it converges to 1/2. So actually it converges to x1. Okay, yeah. Then you just multiply this BC by that, and then you will have the strict inequality for C large. Okay. So now what happens if C is so let's say that this bound is called upper bound is called the M. So this is called C the M. So this is true. So what happens uh if this C is between uh okay, okay. Yeah, so what happens if C is between 1 and okay. Okay. Yeah, we will continue next time for that.